today's topics, we are really super duper focused on exponential models. Okay, so all of these scenarios, I'm not quite sure that's the way to say it, but all of these scenarios is the only way I can really say it, I guess, lead to exponential solutions. So in other words, when we have a differential equation, dy, let's call it dy dx. Actually, let's call it dy dt, because a lot of times they're time focused. Then it looks like, you know, y times t squared or something like that. And the idea is that you have some sort of y to the first power. So this is some sort of y minus 7, or to get really tricky, 7 minus y, and then there's some minus sign. But the idea is that when we separate this, we end up getting like a 1 over y dy equals whatever happens over here. This ends up being a natural log. And the only way to solve for y now is to exponentiate both sides. Okay. The only way to do that. So far, so good. And so now we got to dust off what we know about exponentials. We know that e to the ln y is just y. Notice I'm dropping the absolute values. And if I keep the absolute values, I can put a positive or a negative y in there, right? Because the absolute values would make it positive. Does that make sense? Since I dropped the absolute values, I introduce that possibility by putting a plus minus on that side, my particular solution. Okay, it's kind of like when you square root and you throw a plus or minus on the front. Okay, it's for the same reason. Because whenever we square a number, we end up with always something positive. It's like taking the absolute value of it. Okay? And then this is rewritten as e to the power where we have a variable times e to the power of c, and this is just a constant. Right, 2.71828 to another number is just another number, right? And so what we do is we can say that since this is just numeric, let's just call it big C and put it out front. So you end up with plus or minus C e to the whatever it was that we had as a variable. Okay. So far, so good? Okay. So that's kind of the real general picture. This is covering today and tomorrow, really. Okay. The specific then is this. Today's focus is that I guess not. Okay. I thought I had sneezing. Today's focus is even less complicated. Today's focus is let's just not even have a variable. Let's have some sort of numeric constant, like 5 times y. Okay, so that's this is what we're getting into the takeaways. This is a great time saver. This is the moment where we can skip the calculus. When we see a constant value here, with the y in our differential equation, then we can skip the calculus. We know, and the notes took you through this, we know that this differential equation is some sort of constant times y. And if we know the initial condition, we automatically know the solution. So we can skip the calculus and say y equals, and then we have to have an initial condition. Let's say our initial condition is when excuse me, this no, that should be one. When t is 0, our intercept, so to speak, right? That's what an initial condition is. Our intercept is -3. Then we know that we have -3 e to the 5t. Done. That's our particular solution. Okay. And I took you through an example so that you can kind of see where that goes as we go through all of these steps of separating the variables, grading and giving the actual log and exponentiating and all that stuff. Okay, so this is the day where you recognize that if I just have a numeric value here, I am going to skip the calculus and go right to the solution. That's what they expect you to do. So if on a free response question, they give you this differential equation, part A, they ask you what is the particular solution. They're literally looking for 0 steps. Okay. If they want the general solution, they just want you to put a C here. Here's your general solution. Here's your particular solution. They want 0 steps. They don't want you to do any calculus. A lot of times, and I mentioned this earlier, sometimes they just ask you, hey, what is f of 5, right? Or what is f of 20? Okay, and so they just have you finding function values. So you have to recognize that if you have the differential equation, you have to get that particular solution, and then you can plug in the 20 into the independent variable. Okay. So, from a differential equation standpoint, we're looking for expressions like this to skip the calculus. From a verbal standpoint, we're looking at a phrase like at a rate proportional to the amount present. That's what that means. At a rate that is proportional to the amount present. Y is the amount present. So when you see that verbiage, then you know that you're dealing with a skip the calculus step. Okay. Any questions? Okay. So I kind of changed. This essential question was really long. I kind of paraphrased it, right? When can we skip the calculus and still find a particular solution? When we identify a differential equation that is the rate being proportional to the amount present. Okay, and we have the initial condition. Okay, so we've got topic questions for today. And tomorrow, there's no notes to take for tomorrow. Is that really true? Yes, that's really true. Yeah, tomorrow focuses more on exponential solutions like this. So this is like day 8, and this is like day 9. Okay. Yeah, then that brings us to the end of the unit. Okay. All right. So I'm going to come around. I'm going to check your free response from Friday. Wow. Has it really been since Friday since I've seen you?
Yeah.
Wow. It's crazy. I'm going to check. I'm just going to quickly talk to you about that free response. If you don't have it done, don't sweat it. Just show me what you got done. But it's kind of a super critical free response question. We see that question in some way, shape, or form a lot on AP tests. It's just really a classic sequence of questions. And then I'll check in your notes, and you're going to go ahead and get started on those topic questions.